Very good morning and welcome to Foundations of Continuum Mechanics. Today we'll go through the first tutorial in this course, that is tutorial for the first week. So let's get started. So the topic for this week's tutorial are tensors, indicial notation, summation convention, and Kronecker delta, particularly the substitution property of Kronecker delta. So we'll be solving 10 problems in the tutorial today, and these problems will help you grasp the course and the concepts better, as well as help you solve the problems that will be provided in the assignment, as well as to prepare for the exam. So let us start with the first problem. The problem says that we have to expand Cij. Now the first thing in solving problems like this is to check whether there's a repeated index and whether we can apply the summation convention. So in this case, we can see that the index I appears twice. So we can apply the summation convention. So Cij can be written as sum I goes from 1 to 3 because we live in a three-dimensional world, Cij. And this then we expand. So we write C1 J1 plus C2 J2 plus C3 J3. And that's it. This is the expanded form. There's nothing more we can do here because J is a free index. So this term is general in J, and we have no knowledge of what the quantity C is, so we have to leave it at this stage. So let's try more problems now. So the second problem is that we have to expand and simplify, or we should say just simplify the expression delta Ij times Uj Vi. So again, before we do anything, we will have to expand. But in this case, what we see is that we have a Kronecker delta, and we don't need to expand here because we can apply the substitution property in delta. So because if we expand it, then we'll be wasting our energies, as we learned that we can apply the substitution property here. So in this case, what we see is that the index I and index j, they're both repeated indices in the overall expression. So if you would want to go back to the lecture notes on the substitution property and have a look at its definition, please do that. I'll help you recall. So if an index in the delta appears as a repeated index in the whole expression, then we can get rid of the delta and we can replace the index with the other index of delta. Now remember, the repeated index should be outside delta in the sense that there's an I here and there's an I here. The two indices of delta, if they're repeated, then it's simply equal to 3, as we saw in the last lecture. So let's not worry about that. So we see here, that the index I is the repeated index. Let's do it that way. So the index I is repeated. So in that case, we can get rid of the delta. So in the simplified expression, there's no delta, there's only u and v. And we replace the index I in the remaining expression with the other index of delta, which is j. So this becomes j. This already was a j. So we get a uj vj, which you know is simply u1 v1 plus u2 v2 plus u3 v3. So when we see a delta with the possibility of substitution rule that can be applied, we apply that. We don't expand it because ultimately it's going to result in the same expression. So why waste the energy? Again, with practice, we will learn how to identify these situations. So in this case, if you leave the problem, or leave the answer at this stage, then it's all right. You don't have to further expand because the problem said simplify, not expand. But if you expand it, that is also fine. Right now, many students will ask that why did we take I as repeated? Why not take J as repeated? Well, we can do it. So there's no preference as such. So let's try that. Let's try solving that way. So I'll say another way. So delta ij, uj, vi. So in this case, we say that, okay, the index j is repeated. So we apply the substitution property, which says you get rid of the delta. So there's no delta, there's only u and v. And you replace the index, the repeated index, that is j, with the other index of delta, that is I. So the j that was under u gets replaced with an I. And we already had an I. So ui, vi. And you already know that this also expands to u1, v1 plus u2, v2 plus u3, v3. So ui, vi and uj, vj, they are equivalent because I and j in these expressions are simply dummy or repeated indices. They don't have a meaning by themselves as such. Right, so let's move on to the next problem. So the third problem says that we have to simplify delta ii, delta kk. Right, so in this case, we see that the indices I and k are both repeated, but they appear with the deltas. So we cannot apply the substitution property. Substitution property requires that the indices, two indices of delta are different. So let's write that. That will help us identify the approach. So the substitution property can be applied when the two indices of the Kronecker delta are different. So in this case, the two indices of both deltas are the same, so we cannot apply the substitution property. But we can expand. So delta ii individually is simply delta 1 1 plus delta 2 2 plus delta 3 3, which is 1, because by the definition of delta, if the two indices are the same, it's equal to 1 plus 1 plus 1. This is 3. So delta ii is a 3, and similarly delta kk is also 3, because that's the same thing, just dummy indices I and k. So delta ii times delta kk is 3 times 3, which is equal to 9. So let's try another problem. So the problem says that we have to simplify delta ij, delta ji. So let's see what this simplifies to. Now in this case, we can apply the substitution property. So let's write it down. So which says that if one of the indices of a delta is repeated, then we can get rid of the delta. Now we have two deltas here, and you can see that in the first delta I is repeated, in the first delta j is repeated, in the second delta j is repeated, and the second delta I is repeated. So we have four options to apply the substitution property. The first choice we have to do is which delta should we take and get rid of, and the second is which index of the delta we have chosen is to be taken as repeated. Now the beauty is that you can do anything. You can choose any one of the four choices and you will still get the same answer. I'll show you by taking a couple of choices. So let's take so the first delta as the delta for applying the substitution property. Take first delta and take I as repeated. So I'll write the expression. So delta ij, delta ji. So what we have done is we have taken this as the delta and we have taken the index I as the repeated index. So as per the property, what we do is we get rid of the delta. So we get rid of this one, and what we are left with is an expression which is the remaining part, that is this delta, and the repeated index in the remaining expression is where in that expression I is replaced by j. So this becomes delta jj. So here there was an I that's replaced by a j, and this we already know is a 3 from the last problem. And as I said, whatever choice you take is going to result in the same answer. So let's take the second delta and take j as repeated. So in this case, we'll take this as a delta and we'll take j as repeated. So what will happen is that when we apply the substitution property, the delta will vanish. So the delta we have is this one. So this will go, and what we are left with is the remaining part, which is in this case also a delta, and the repeated index, that is j, is replaced with an I. So this becomes delta I, which is also a 3. So I request you to please pause this video and try the other two options, where you take the first delta with j as repeated and the second delta with I as repeated, and appreciate the fact that all these choices result in the same expression. So let's try the next problem. Problem 5. So we have to simplify this expression. Now this has 3 deltas this time, and we can see that whatever delta we choose, both its indices are repeated. So the first delta has indices I and j, and we can see both I and j are repeated in the whole expression, in the whole mathematical term. In the second delta we have j and k, both j and k are repeated, and the third delta has k and I, and both k and I are repeated in the overall mathematical term that involves the 3 deltas. So again, as I said, that the choice is yours, you will get the same answer. So we go from left to right. So we'll take the first delta on the left as the delta and the remaining expression as the expression which is considered to be some expression. So we will take the first delta and let's take I as repeated. So we'll say take first delta and the index I as repeated. So the expression delta ij, delta jk, delta ki will simplify to, so we have this as the delta, and we have I as repeated. So we'll get rid of this delta in the simplified expression. So what we are left with is delta jk and delta ki, but we have to replace the repeated index, that's k, with the other index of the delta that we have taken, that is the other index is j here. So this k gets replaced with a j. This is not the final answer yet, because we still have two deltas and we can still apply the substitution property here. So what we'll do is we'll take delta jk as the delta for applying the substitution property, and we will take the index j as repeated. So the expression that we had, delta jk times delta kj, this will reduce because we have, this is taken as a delta and the index j is taken as repeated. So we have delta kj left, but we are replacing j with the other index, that's k. So this becomes delta k. Right? Now this can simplify further because delta kk is simply equal to a 3, because when you expand it, it becomes delta 1 1 plus delta 2 2 plus delta 3 3, which is equal to 1 plus 1 plus 1, which is a 3. So this is the final answer. So this whole expression, delta ij, delta jk and delta ki multiplied together is equal to a 3. And see, these problems that I've given are usually expressions you experience when you're trying to solve problems in tensor algebra and tensor calculus. So we will see these expressions that will appear in front of us. So these results that we are getting will be useful. But of course, you don't have to remember this. You have to learn how to simplify using the rules such as summation convention and substitution property of the in the indicial notation in tensors. So let's move on to the next problem, which is problem 6. Now this is a problem that has been provided to confuse you a bit, because we have two deltas multiplied together, but this time there's only one index that is repeated. So if you choose the first delta as the delta for applying the substitution property, you can only take j as the repeated index because I is not repeated. Similarly, if you chose the second delta as the delta for applying the substitution property, then only the index j is repeated, k is not. You can still choose any of the deltas, but the repeated index has to be the one that is actually repeated. So let's choose the second delta as the delta. In fact, let's do it left to right. That's what typically I do. So this is taken as the delta, and we take, well, there's only one option here, that j is repeated. So I'll suggest you, when you try it, you try to take the second delta as repeated, but I'm taking the first one. So this simplifies to, so we get rid of the first delta, so we only have the second delta left, that is delta jk, but we replace the repeated index, that's j, with the other index, that is I. So this becomes delta I k. And there's nothing we can do further with this, because both indices of this delta are free indices. So there is no further simplification that is possible at this stage. So we leave it at this. So let's go to the next problem. So this is a true or false kind of a problem where it's asked, is it true that ei dot ej is equal to ej dot ei? Now, of course, you know that the vector dot product is commutative. So this is true. But we can also see this from the angle of the Kronecker delta, because we know that ei dot ej is equal to delta ij. Again, you can go back to the lecture notes and have a look in the previous in this week's lectures. But I can help you recall. So ei dot ej is only equal to 1 when the two indices I and j are the same, because EIs are unit vectors and they are linearly independent because they are they form a set of orthonormal bases. So E1, E2 and E3 are the three mutually perpendicular directions in the right hand Cartesian coordinate system. So this is E1, this is E2 and this is E3. So ei dot ej will be equal to 1 only if I and j are equal, and that is the same as the definition of the Kronecker delta. So ei dot ej is delta ej. Similarly, ej dot ei is going to be delta ji, but we already know, or we can see easily, that delta ij is the same as delta ji, because by the definition of delta, let's write it down. So this is equal to 1 if I is equal to j, and this is equal to 0 if I is not equal to j. So we can see easily here that the definition of delta does not depend on the order of the indices I and j here. So delta ij is equal to delta ji, and by that logic, using these two expressions that we have written, we can see that ei dot ej is the same as ej dot ei. So the answer to this problem is yes. So let's move on to the next problem. It says state true or false. The statement is scalars and vectors are tensors, and this is true. Why? Because scalars are actually 0th order tensors and vectors are first order tensors. And this is how we learned about tensors. We started with an intuitive understanding by defining scalars as 0th order tensors, because we need only a magnitude in this case. In vectors, we need 3 components, and in higher order tensors, depending on the order of the tensor, we need 3 to the power of n components. So if n is 0, that is in scalars, we need 3 to the power of 0 components, which is 1. We need 3 to the power of 1 components, that is 3, and in higher order we need 3 to the power of n components to describe the tensorial quantity. Right. So the statement that scalars and vectors are tensors is true. So the next problem says there is an expression given to us which is sigma ij times ej, and there are two parts to the problem. The first part says that the index I is the dash index, and we have two options to be chosen from: free slash dummy. The problem B says that the index j is the dash index, and again we have the same two options, free slash dummy. So again, think about it. You already know the definition of free and dummy indices. So in the expression sigma ej, the index j is repeated or dummy. So we answer the part B as j is the dummy index, and the index I is free because it appears only once in the mathematical term. Now I keep replacing expression and mathematical term because we only have one term, but if we had multiple terms in the expression, then we'll have to deal with each and every term separately. So in this case, since we only have one mathematical term in the whole expression, we don't need to specify the term separately, but we can see that I is a free index in this case because it appears only once. So now we move on to the last problem of this tutorial. That's problem 10. So the number of components in an nth order tensor are, and we have four options. The first option is 2 to the power of n. The second option is n squared. The third option is n cubed. And the fourth option is 3 to the power of n. So in an nth order tensor, the number of components, well, let's say sigma ij is a second order tensor. So we take an example. And we have two indices, I and j. I can take values from 1 to 3. J can take values independently from I from 1 to 3. So we have a total of 3 times 3, 9 combinations possible. And we've already written this as a matrix as sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, and sigma 3, 1, sigma 3, 2, sigma 3, 3. So we have 9 components, and that is basically 3 times 3, which is equal to 3 squared components. In a third order tensor, Cijk, we have 3 independent indices. So we have a total of 3 times 3 times 3, which is 3 cubed components. So we can see that the general expression will be 3 to the power of n for an nth order tensor. So the answer is D, 3 to the power of n. Now, some people may get confused that the first option, option A, is 2 to the power of n. But that will be true if we live in a two-dimensional world. But as I mentioned, and I've been mentioning again and again, that we live in a three-dimensional world, and therefore we will always assume that the indices of a tensor can go from 1 to 3. And we also draw our Cartesian coordinate system as with the 3 basis vectors E1, E2 and E3. So unless it is specified otherwise, we'll always assume it's a 3D world. So the number of components is 3 to the power of n, not 2 to the power of n. So that brings us to the end of this tutorial. I hope after these 10 problems, you have got some understanding and confidence in working with mathematical expressions that involve tensors, with indicial notation involving summation or repeated indices, applying summation convention, and the use of Kronecker delta's substitution property. I will repeat for the nth time that practice is what will make you perfect. So please practice problems. Try to do these problems even after looking at the video yourself so that you are able to solve the assignment with confidence and solve the problem towards the end of the course correctly as well. So thank you, and I'll see you next week in this course.